All right, so we are in your workbook. This is the section called Logarithm Logic. We've been calling this, I guess we're up to 5.6 right now, Logarithm Logic. So this starts off with, it continues on with from the logarithm laws that we looked at in the last couple of lessons. And those logarithm laws state that, and these are on your formula sheet. And the first one says the logarithm of m times n is equal to the logarithm of m plus the logarithm of n, both base a. So there's your product law for logarithms. And sometimes we will take a logarithm and we'll break it apart. We'll take the product and break it apart into the two pieces that add together. And sometimes we'll have the two pieces that we combine together into a product when we simplify and make it one logarithm. The second rule was that the logarithm of m divided by n base a is equal to the logarithm of m minus the logarithm of n. The nth logarithm is subtracting, it's negative because it's in the denominator of your ratio of m over n. And in fact, if we had the logarithm of 1 over n, this would just equal the negative logarithm of n. The third rule that we looked at was, let's stay down, I'm running out of room here a little bit, the logarithm of m to the power, to the exponent of n base a is equal to that exponent of n comes down front, and it's now a coefficient of n times the logarithm of m, all base a. So those are our three rules for logarithms, and we looked at those in the last section. We looked at a couple of other things that I should just briefly mention. One of them is that the logarithm of b divided by the logarithm of c in whatever base that we want, that's going to be equal to the logarithm of b base c. And so there's your change of base rule. This can be done with any base. So if we have the logarithm of b base a over the logarithm of c base a, as long as that number is the same, then we can change it just into base c logarithm of b base c. The last piece that I just want to mention is it also tells us on your formula sheet y is equal to a to the x is equivalent to x equals logarithm of y base a. And the critical piece when looking at those two things is that a is the base of the exponent. It's also the base of the logarithm. The other two letters, they change places. In the first one, the x is in the exponent. In the second one, the y is in the logarithm. And that comes very handy when you're trying to solve for an exponent, or if we're trying to solve for something in the logarithm. All right, so all of that said, we need to now put together some kind of advanced rules. And some of these kind of end up being automatic consequences of those three things that we've said. And some of them end up being, we have to put a little bit more thought into it. And the first one says, okay, well, what if we have logarithm of 1 base 7? As mentioned in the notes, it is telling us that this is not on your formula sheet. You should know these. Some of them are a little easier to get your head around than others, but this one's not too bad. The logarithm of 1 base 7. Remember that what a logarithm is it's answering the question, 7 to what power is equal to 1? This question, log of 1 base 7, is the same as 7 to the what is equal to 1. And that, of course, is 0. Anything to the 0 is 1. Logarithm of 1 base 3 is saying 3 to the what is equal to 1. So those are both 0. So we have a rule that logarithm of 1 base a, base anything you want, is always going to be equal to 0. The next line says logarithm of 7 base 7. So that's saying if we swap that around into exponent form, 7 to what power is 7? And of course 7 to the 1 is 7. Log 5 base 5 is 1. 5 to the what is 5. A to the what is a. And those are just all equal to 1. Now, this third one, logarithm of -1 base 7, that's equivalently stating 7 to what exponent is equal to -1. And if we think about our exponential curve that had a horizontal asymptote and it looked like this, for any value of x, will that ever equal -1? Ever be down here? And it won't. We have this horizontal asymptote. The value of 7 to any exponent will always be a positive number. And so what we call this is we say that this is undefined. Logarithm of -5 base 2. 2 to the what is -5? It never is. Undefined. And in fact, the logarithm of negative anything base a is always undefined. We could also look at that with the graph of logarithm. And we saw earlier that the graph of logarithm looks like this. It had a horizontal asymptote, or sorry, a vertical asymptote. And so the domain of that is x greater than 0. It has to be strictly greater than 0. It can't equal 0 because that's the asymptote. So the argument for logarithm, what's in the brackets, has to be a positive number. So therefore, what we're saying is logarithm only works when that's a positive number. Okay, so here's a few of our kind of simpler rules. Logarithm of 1, doesn't matter what base it is always equal to 0. That ties into the fact that whatever base we're using, the graph of y equals log x is equal to 0. Logarithm of 7 base 7 is equal to 1. Logarithm of a base a is equal to 1. All right, in this next, this is looking at something maybe a little thicker. 10 to the log 5 and 10 to the log 2. Now keep in mind that when we don't have a base number written in the logarithm, we're going to have a tiny little subscript in there of 10. This is 10 to the log 5 base 10. And the next one is 10 to the log 2 base 10. And so we're trying to come up with a rule. Now, if you push these into your calculator, 10 exponent log 5, you'll find that that's equal to 5. You'll find that this one is equal to 2. And so therefore, the logarithm of x, or sorry, a to the exponent of log x base a will equal x. Now, there's a few different ways we could look at this to kind of come up with this rule about why it is. And if we say, well, I've got a to the log x base a, and I want to know what it's equal to. For now, I'm just going to say it's equal to y, and so that will be my answer when I figure it out. If we start with this, and then we swap this around. This is now in exponent form. So if I swap that into logarithm form, so our next step when we swap this around into log form ends up being the logarithm of y base a is equal to that exponent of log x comes down, and it's this. And on the left side of this equation, we have log y base a. On the right side, we have log x base a. So therefore, y is equal to x. So therefore, this amount is equal to x. A to the exponent log x base a, as long as that base is the same, then that will be equal to the argument of the log. All right, in this next line, this one ends up being a little bit, fair bit simpler. Logarithm of 2 to the x base 2. And this is just going to use our power law. It's going to use our power law for logarithms. And let's say that this ends up being x times the logarithm of 2 base 2. That ends up being x times 1. So the logarithm of 2 base 2 is just 1. So this ends up being equal to x. The logarithm of 6 to the x base 6. That 6 comes down front, ends up being x times log 6 base 6. This is just equal to x. So we end up with another rule. This will equal x logarithm of a to the x base a. As long as that a as the base and as the other base, I suppose, as long as they're the same number, those will be equal. And then if we have radicals, if we have roots in here, remember that square root 2 really just means 2 to the half. And if I think about it this way, then that half comes down as a coefficient times log 2 base 2. And so this just ends up being equal to 1/2. Similar by this, log of cube root 10. That's really the same as logarithm 10 to the third. We bring that 1/3 down front times log 10 base 10, which is just 1. So this ends up being equal to the logarithm of a to the nth root of a is 1 over n. Because converting it to an exponent, that's what it'll be as a power on a, and using your power law, that's how it simplifies. So question number 1. Evaluate the following. Log 3x base 3x. Super easy, it's just 1. Logarithm of 3 to the 4 base 3. It's just equal to 4. It's just equal to 4 times log 3 base 3, which is just 4. You want to kind of keep in mind throughout all of this that what a logarithm really is, and we discussed this in the other video, that this relationship between these 3 numbers, and you could use any 3 numbers that work like this. 2 cubed is 8. We learned that way back in probably in junior high. And if that's true, then the cube root of 8 will equal 2. And if those are true, then the logarithm of 8 base 2 is equal to 3. So just a reminder that this is really all that a logarithm is. That a logarithm is just kind of this, it's this power notation. The power of 2 is 8. Well, that's 3. And so if you keep that in mind, that will help streamline how all of this goes. Be careful that we don't start to write this so it looks like the 8 is an exponent of 2. When we write a logarithm, the argument is 8. 8 is the number that you're taking the logarithm of. 2 just happens to be the base, and it's this little tiny subscript. So the 8 is a regular size 8. The 2 is a subscript as our base. All right, so the next one. 4 times logarithm 6 base 2 to the logarithm 6 base 2. So this just ends up being 4 times, and we saw this right above here. And as long as that base of 2 is the same as the base of the exponent of 2, This is equal to 6. Gives us an answer of 24. We can treat logarithms kind of like we were treating exponentials. If we can get things expressed as the same base, that is helpful. We know that 25 is 5 squared. So this is 5 squared to the k, logarithm of 5 squared to the k, base 2. Typically, we would write this as 5 to the 2k, and from that, this ends up being 2k. Probably don't need to express that as log 5 base 5 at this point, because we know that that part is just equal to 1. This is 2k. In part B, this is the logarithm of a to the 1/2 the x. This is all base a. That exponent is x over 2. We bring that down front. There it is. This is equal to x over 2. Hint, when the logarithm base and argument are the same value, this can be easily simplified. Just to remind you, because we haven't used that word argument very often in math class in the last few years, but when we're talking about an argument in mathematics, it's like we have some sort of symbol, like square root. That isn't complete. We can't just have a square root symbol by itself. It's asking for an argument, whether that argument is x, or square root of 7, or the square root of 7x. That symbol, square root, isn't complete without its argument, without the thing that we're taking the square root of. We've seen this in other forms before. We've seen sine, or cos, or tan. And we've seen where we have to take sine of a number or some sort of object. And so if we have sine of 30 degrees or something like this, that 30 is your argument for sine. Same thing with logarithm. Logarithm needs an argument. So, next page. Simplify the following. We can do this a couple of different ways. A lot of these questions actually can be done in more than one way, and I'll show you different ways to approach these things. If we have logarithm of a to the 7 base a plus logarithm of a cubed base a, one way of doing this is calling this 7 log a base a. Use your power rule, bring that exponent down front. And we have 7 of log a base a plus 3 of log a base a. Whether we add them together and get 10 log a base a, or whether we call this 7 plus 3, because log a base a is just 1. This ends up being equal to 10. We can also do this by putting them together and taking log a to the 7, log a to the 3, each of them base a. And if we use our product rule for logarithms, now let's multiply them together. This is a logarithm of a to the 7 a cubed. This is the logarithm of a to the 10 base a. So we could get 10 that way. Some problems might be faster one way than the other, but both are equally correct. In this case, we have these logarithms. We have different arguments in them. So let's bring that 4 inside the logarithm and call this the logarithm of x y cubed, all to the 4, minus logarithm of x squared y to the 6, all to the 2. So just bringing those coefficients inside. And now this is equal to the logarithm of x to the 4 y to the 12 minus logarithm distributing this exponent is x to the 4 y to the 12. This is just equal to it's just equal to 0. We have the same amount. We're subtracting logarithm of x4 y12, subtract log 4x, subtract log of x4 y12. It's positive 12 minus 12. Like it's just, you're subtracting two things. And so that's equal to 0. Another way of showing that it's equal to 0 is we could use our logarithm laws. Maybe a couple more steps, but we could change the subtraction into a quotient. And now we have the logarithm of x to the 4 y to the 12 over x to the 4 y to the 12. Anything divided by itself is just 1, and this is now equal to the logarithm of 1, which is 0. So either way it works. This one's not too bad. I'll give you a minute. Maybe you can try this one with your product and your quotient laws for logarithms. So maybe hit pause and come right back. All right. So hopefully you realized we have a logarithm. All three of these logarithms are base b. This first one is positive 6x cubed. This next one we're adding log x to the 5. So let's express that as a product. And then we are subtracting, this one here is negative, logarithm of 2x squared. This is all base b. And we now can just simplify that expression. So the logarithm gives us 6 over 2 is 3. X to the 8 over x squared is logarithm 3x to the 6. This is base b. All right, in this next one, a couple of extra wrinkles thrown at us. We have x to the half is your square root, but we're bringing that coefficient of 2 inside, so it's the logarithm of x to the 1/2 to the 2. We have this term is subtracting, so we're going to bring that. Maybe I'll do this in an extra step. Maybe I don't need to try to do everything all at once. So let's call this minus log of 3x squared all squared, and then minus logarithm to the 5. So that's just bringing your coefficients into the logarithms. Now we have 3 logarithms. They're all the same base. They're all base 10. And so we can write this as logarithm of x to the 1/2 squared is just x. We are subtracting this second term. So this is 9 x to the 4. 9x to the 4. And then x to the 5 also downstairs because they're subtracting. So any term that ends up being a negative will end up in the numerator. Any term that ends up being positive ends up in the numerator. Numerator for the positive leading coefficients. Negative coefficients end up being in the denominator. We can take this a step further and simplify it a bit, and this ends up being equal to logarithm of 9x to the 8 downstairs. Nothing left upstairs, so we'll call it 1. So when simplifying logarithms, let's make the coefficients. The coefficients into the exponent. first. It's a good first step. All right. So now let's use some logic and apply all of these things that we've learned. This is going to harken back to some of the previous chapters that we've looked at. Lots of crossover with transformations. The graph of f of x is equal to 5 to the x minus 1. We can think of this as your y. It's transformed to become y is equal to f to minus 1x. Remember that this means inverse. This means an inverse function. We are undoing that function. When we dealt with this algebraically back in transformations, you swap your x and y. So therefore, this first statement of y equals 5 to the x minus 1, if I want the inverse of y is equal to 5 to the x minus 1, that is x equals 5 to the y minus 1. So you swapped your x and your y, that's now the inverse. Your domain would become your range would become your domain. All of your coordinates would swap coordinates. And so this is now our function. That is its equation. We probably should simplify it by getting y by itself. How do we get y by itself? Right now it's in the exponent. Well, so we swap around to log form. We swap this around to log form. And technically this is the same as just taking the logarithm of both sides. So we can look at it that way. Log x is equal to the logarithm of 5 to the y minus 1. Log x is equal to, exponent comes down front, y minus 1 times log 5. Distribute. Log x is equal to y log 5 minus 1 log 5. Just distributing into this bracket. Add log 5 to both sides. Log x plus log 5 to y log 5. And our last step, just to divide everything by log 5, we end up with y is equal to log x plus log 5 over 5. Now that would probably be good enough for an exact value final answer with this. However, you should be aware that, especially on a multiple choice test, you could see things that are in different forms, and you need to be able to translate this into the next form. Even though you might argue that this is simplified, there's some things that we can do to this to take this further. We could take log x plus log 5 over log 5 and break it apart into two fractions and call it y equals log x over log 5 log 5 over log 5. We take it a step further. This second term is just 1, right? This other piece, log x over log 5, there's your change of base formula. We can just tidy this up half a step and call it log x base 5. And so that's probably an even slicker form of this answer is log x base 5 plus 1. Question number 2. If we have If we're being told that logarithm of 4 base 3 is equal to x, well, if you think about what that means numerically, log 4 base 3 means 3 to what power, 3 to what exponent is 4, and 4 is a little bit more than 3. It's certainly 3 squared is 9, so I don't know, something like 1.2 or something like that. But for now, we're just calling it x, because we're wanting to write an expression for this, log 16 base 3, in terms of x. So to do a question like this, let's start with that log 16 base 3 and claim that log 16 base 3. Let's show what it's equal to. Let's use our logarithm laws and show what that's equal to. We're trying to integrate this x, which is log 4 base 3. So there's our hint that we want to change this to something to do with 4. And we know that 16 is 4 squared. So we're replacing 16 with 4 squared. This is equal to logarithm of 4 squared base 3. We also now know that that's the same as 2 log 4 base 3. But that's our definition of x, is log 4 base 3. So this is equal to x. We have expressed this thing in terms of x. Number 3. Given that log a base 3 is 6, log b base 3 is 5, determine the value of log 9ab squared base 3. There's a couple of different ways of doing this. Personally, I would prefer the approach. Let's start with what we're trying to express. We're trying to find the value of log 9ab squared base 3. So let's start with that. And then let's modify it and show what it's equal to. Well, we know that that's equal to log 9 log a log b squared. All of them base 3. This logarithm of 9, well, whether you convert that into log 3 squared and then the 2 comes down front, or whether you just realize 3 to the what exponent is 9. This is equal to 2. This next term, log a base 3, we're told that's equal to 6. This log b squared, we have a little bit more massaging to do with this. Let's call it 2 log b base 3. And so this will be equal to 2 plus 6 plus, what do we have? We have log b is 5. So this is all equal to 18. That's kind of how I would approach a question like this. I would start off with what we are trying to enumerate or simplify, and then just show that it's equal to those other pieces. We could take an approach like this. We could, however, if we'd rather, let me do this in a different color. If log a base 3 is equal to 6, that tells us 3 to the 6 is a. If log b base 3 is equal to 5, the equivalent form to that is 3 to the 5 equals b. Then logarithm of 9ab squared, all base 3, will equal logarithm. Well, that 9 is 3 squared. And a, we've just said, is 3 to the 6. And b, we've said, is 3 to the 5. And so we have b squared here. we simplify this out. This ends up being equal to logarithm of, if we're counting the exponents so that we add them together because they're multiplying, 2 plus 6 plus 10 is 3 to the 18. And this is equal, this is base 3, so therefore this equals 18. So we get the same answer from a different way of approaching it. Either is fine. Number 4. If log A is equal to 3 base m and log B is equal to 4, then log of 1 over AB. Oh, we could do this in those two different approaches also. How about I do this in blue to show that it's same. And let's start with logarithm of 1 over AB base m. This is equal to logarithm of a minus 1, b to the minus 1 base m. This is equal to logarithm of a to the negative 1 plus logarithm of b to the negative 1. Both of them base m. And then this is equal to negative log a m minus log b base m. So just bringing those exponents of negative 1 down front, write them as your coefficients. Notice that a and b were both in the denominator, so those are both now just negative. And this ends up being equal to negative of 3 minus 4 equals negative 7. Now, if instead we took log of a, it's m, equal to 3, therefore we swap this around into exponent form. M to the 3 is equal to a. Similarly, because log b 4, m to the 4 is equal to b. Therefore, logarithm of 1 over ab base m is equal to the logarithm 1 over m cubed m to the 4 base m. This is equal to logarithm of m to the negative 7 base m, which is equal to negative 7. So kind of either approach to get there is fine. Either approach to get there, either swapping it around into exponent form, or what we did first in blue was just evaluating that expression. Question number 5, though, really works better with that second form of swapping it around. Just because I'm not quite sure what I'm going to do with log b base a plus log a base b. So instead, let's solve for a, and let's try to enumerate what a is. Log 8 base a is equal to 3 is the same as saying a cubed is 8. Raise both sides to the exponent of 1/3, or cube root both sides. And we get a is 2. logarithm of b base 4. 3 halves, 4 to the 3 halves is equal to b. Well, whether you push in 1.5, 4 to the 1.5 into your calculator, whether you take the square root of 4 first and you get 2 and then you cube it, either way, b equals 8. And now we can evaluate log b base a, log a base b. Becomes log 8 base 2 plus logarithm of 2 base 8. This first one is just 3, because 2 to what exponent is 8? 3. A little trickier is 8 to what exponent is 2? Well, we know that 2 is the cube root of 8. So we could call this logarithm of 8 to the 1/3. Here's your cube root, which makes it 2. And so this ends up being equal to 3 plus 1/3 times log 8 base 8. The nearest hundredth is 3.33. Make sure you follow instructions that you have about rounding. That often gives you a clue that, oh, I should be picking up my calculator for this at this point. Perhaps I should be graphing. Not in this question, but just watch for that when you ever have rounding instructions. Number 6. Logarithm of 2 sine x over sine 2x. So your first thought is, how horrible is this? You're going to not only mix up the units that we've done in this course, but you're going to make me responsible for figuring out what to do with sine 2x. So sine 2x, that's one of your double angle identities. These are on your formula sheet for any exam that you have in this course. So you need to recognize that sine 2x is on your formula sheet and then be able to dig it up, know where to look for it. Sine 2x is the easy double angle. Cos 2x is the one that has 3 different manifestations of which to pick. So therefore, this is equal to the logarithm of 2 sine x. You go into your formula sheet and you realize that sine 2x is 2 sine x cos x. Taking the logarithm of all of that. This all divides out because this is just an expression inside the argument. Be careful. If you have log 2 sine x divided by log 2 sine x cos x, this is an entirely different thing. And you cannot just divide out this factor. But in this case, we can. Right? We have 2 times sine x over 2 times sine x cos x. This is equal to the logarithm of 1 over cos x. Now you might think, oh, I know that to be secant. So you'll start looking for secant in these answers here, and you don't see any secant here. But you do realize that cos x to the negative 1 is the same as 1 over cos. And so therefore our answer ends up being D. We bring that negative 1 down front, and it's just D. All right, almost done here. Number 7 is an interesting question. In that it says, okay, so this function, log x is base 2, is transformed into log 32x base 2. Describe your transformations that has occurred in 2 different ways. The more apparent one is to call this that x has been replaced with 32x, therefore it is a horizontal horizontal stretch, axis, factor. This is where we have to be careful in here. This is a horizontal stretch, so the factor is the reciprocal of that b value. So it's a stretch factor of 1 over 32. There's the clearer one. The less clear one takes into account what we know in this chapter, that if y is equal to log 32x base 2, that this is equal to the logarithm of 32 plus the logarithm of x, both base 2. 32 is a power of 2. It's 2 to the 5. So we could write that step, or we could just ask ourselves 2 to what number is 32? This is 5. So we have 5 plus log x, the same as log x plus 5. This is a vertical translation. Up by 5. Which actually ends up being kind of super interesting. If we compare, if that's our graph of y is equal to log x base 2, if I horizontally stretch it by a factor of 1/32, and it's going to look like this. Everything has been stretched or compressed to 1/32 its amount, and it's going to kind of look like that. And so what we're saying is, if we took that same curve and shifted it up by 5, it's going to be the same curve shifted up by 5. Those would be the same, which is actually kind of interesting to think about it. All right, last one, number 8. So again, with this theme of incorporating stuff that we've done earlier in this course, given that f of x is 3 to the x, and g of x is log 27x base 3, describe the simplified form of f circle g of x. So f of g of x, remember that f circle g of x is composition of functions. G is your inner function and f is your outer function. If we write it like this, then this is really just f of, now let's replace g with what it is, logarithm of 27x. We could simplify that a little bit, and let's call this the logarithm. So f of, let's leave that f alone for now, and let's call this the logarithm. We're going to break that 27x apart. Logarithm of 3 cubed base 3. That's the logarithm of x base 3. So I did two things in that step. I broke apart the 27 into x, and then I called 27 as 3 cubed, so that this is equal to f. This whole first expression is just 3 log x base 3. Now let's take that input and for your function f. And your function f says 3 to the x. So 3 to the 3 plus log x base 3. Which ends up being equal to, we're adding these two things in your exponent. So this is really just 3 cubed times 3 to the log x base 3. It's just 3 cubed times 3 log x base 3. That first factor is 27. And the second factor, 3 to the log x base 3. Remember back at the beginning, we kind of looked at that. If we have 3, if we have any number raised to the logarithm of x base, that same number, this is just x. So that's pretty much it. I would throw out to you the fact that we could look at this maybe in a simpler way, that f of g of x, g is your input. If this is f of 27x base 3, if I compose that with the function f at this point, the function f is just 3 to the x. So let's go 3. That's my exponent. Well, by following the same rule that we just did here, this is just 7x. And we get the same thing. All right. So good luck with your practice questions. If you have any questions, please ask. Thanks so much.